In this video we're going to build one machine to rule them all. A 9-axis monster for screw counting. And I'm going to give an update on everything else that has happened since my last video. And buckle up, because this is a long one. During the last years, I've manually packaged and counted thousands of different screws, nuts and washers. All for 3D printed parts that I sell online. So I used 3D printing, PCB design and other processes to build an automatic screw counting machine. The design is based on some fundamental principles and it is parametric, so it should work for a variety of conveyed parts. In this video series, I will go over the components and how I built them. If all goes well, the videos will end with a working modular production system. Around half a year ago, we had to change our business model. Basically, we went from selling machines to selling bags of packaged fasteners. And over the last 6 months, we went through hundreds of thousands of screws and actually made an entirely new machine for this. But let's first take a look at how the old feeder worked and how and why we had to change it so drastically for volume. In the original feeder, parts were not only counted, but also oriented. For this purpose, there were parametric components specific to the screw. Overall, it's not a lot of work to set up a different fastener, and most of it is done in parametric software. But it still means that each feeder has to be tuned to its specific screw. If we want to feed more parts, we need to build more feeders. This one feeder per part logic was perfect for feeding because you usually work with the same part for years. But when we stopped feeding and started kitting, we suddenly had a much higher mix of fasteners. And as you will see, this became a huge problem. About 6 months ago, we started offering a kitting service. For many companies and projects like SwapMod or OpenScan, we packaged thousands of small bags of fasteners. The first thing that I had completely underestimated was the variety of parts. It's hard to imagine how many different screws there are. It's really hard to visualize this, so here's a quick example. This is an M3 cap-head screw. It comes in at least 20 different lengths. All of them also exist in different materials. For example, you can get them in blank steel or zinc coated. These variations split again into at least 3 different material grades. Also, let's include stainless steel options. All of this variety then doubles for different drive options, and then doubles again for full or partial thread, and then everything doubles again for lower head profile. Well, you get the idea. This madness then repeats for all thread sizes across each fastener type. And I had completely underestimated this. With the old 1 part per feeder logic, we would have had to build at least 250 feeders just to get started with the first customers. So it became clear, we need a different solution. This is no longer about feeding and orienting the exact same part over and over again. This is high mix counting, much higher mix than I expected. There's really only one solution for this, and that solution is to build a much smaller line with a few universal counting machines, each of which can count all of the parts. We let it run for 2 hours, kit 10,000 bags for one customer, and then swap the parts to make 1,000 bags for the next kit. But if you think about it, this is not super easy. Ideally, we want each module to be capable of counting all fasteners. From an M2 countersunk to an M8 cap head, wood screws, nuts, washers, you name it. Counting parts of such a range on the same machine is a bit of a challenge, but I have an idea. This is the machine we came up with. It has 9 axes, and admittedly it's a bit of a monster. A box with fasteners gets placed here. It moves on a simple printed slider that is lubricated inside of the T-slot profile of the aluminium extrusion. The entire counting mechanism tilts down and locks onto it. Next, everything tilts up. The screws inside are supposed to travel along this path. They get counted in this area, more on that later, and then fall into this buffer bucket. The bucket is mounted on a load cell. This is a second, completely redundant counting method, and it speeds up counting for large quantities. During normal operation, the counted screws simply fall out of the buffer. If something goes wrong for any reason, there's a flap to discard parts. There are a lot of sub-assemblies, but it's much easier to understand on the real thing. So let's test it. Assembly this time was way too much work to film it, so we're gonna have to dive right in. Unloading a box is similar, but we give it negative tilt to flatten the pile of screws inside. Many of the 9 axes in this machine move simultaneously, and I really don't want to know what this would have cost to build in traditional industrial electronics. Before I explain the whole machine in detail, here is the same loading process from a different perspective. Now, you probably have a lot of questions now, so let's dive right in. The box is placed. There is an RFID tag on each box. The machine scans the tag and pulls all of the parameters of a screw, such as length, diameter, weight, and so on, from a central database. Next, the loading process begins. A box with parts is brought in. It gets locked and lifted. It is critical to lock the box well without any gaps. Otherwise, parts will escape and get stuck. For the clamps, I chose a simple but surprisingly effective mechanism. 3 sloped discs rotate in and press the box into place. I don't know how well this translates on video, but it generates quite a lot of force, and since we press it against the rubber seal, this creates an extremely good connection. Speaking of power, the tilting movement is driven by two linkages mounted on ball screws. This can handle a full box of fasteners, which is about 20 kilograms, without any problems. Okay, but now how does the part counting work? It's easier to show you and then explain. So how does it work? First, the screws are arranged into a row through a series of plate movements. Next, the feeder detects the exact position of each screw. It counts them from left to right. Depending on how many parts should be dispensed, it moves to the corresponding height. The exact motion profile is loaded automatically and differs depending on the part and its size. For example, we use a different pattern for nuts. I have never seen anything close to this in industry, but it works extremely well. In fact, we could make it much faster before the screws get ballistic. You can see it even better in the top view. Let's say we want to dispense 10 screws. But how does the feeder detect the exact position of each part? Well, that was one of our brighter cost-saving moments. If you've ever looked inside an office scanner, you may have noticed its image sensor. It's basically a line camera that moves along to scan the paper. As it turns out, you can buy just the image sensor as a spare part. This is one of them. We connected it to our board, which pretends to be an office printer. When we turn it on, we can see that it can easily detect an object. Now, so far, this is nothing spectacular, but what I find absolutely crazy is the resolution that we can achieve with it. Each millimeter of the scanner has 48 pixels, which means that across the entire 20 centimeter length, we have a resolution of about 40 micrometers. And it costs 10 euros. Now, admittedly, we are binning and are using only about half the resolution possible. And we had to do a couple of tricks to manage the data rate with our small microcontroller, but I still think it's an amazing sensor. Inside the feeder, there's one of them that scans the screws. The only thing that we could not really solve is that there are tiny scratches that form in the acrylic. And after a while, this becomes a problem for the scanner. We filter some of them out in software, but when the sheet gets too scratched, we have to swap it. Depending on the fastener types, this happens about every 100,000 parts, so it's still okay, but acrylic is really a terrible choice for this. Ideally, what I want to use is diamond-coated glass, like it's used at supermarket checkouts and their scanners, but I don't have a water jet cutter and I cry myself to sleep every night over it, but there's really nothing we can do except swapping the sheet every now and then. Okay, so the parts have been counted by the scanner. What happens next? They fall into this buffer chamber and are weighed. If the correct number is reached, they fall through. If, for whatever reason, incorrect amounts are detected, the parts are discarded. The transparent hedge is locked by an over-center linkage that is decoupled from its actuators. Decoupling is necessary to measure the exact weight of the buffer, because cables attached to it would distort the load cell measurement. Normally, several of these machines and a conveyor belt would be combined. This allows any combination of parts to be achieved. In the interest of keeping this video somewhat contained, I will need to skip over a few details, such as the puncher mechanism or the crazy length we went to in order to prevent panel gaps. However, there are still two things I would like to point out. The first is that we can count almost any fastener on this machine. We tested so many parts, almost everything works. Literally every single box we have can be counted on the same machine. Good luck trying that with a vibratory ball feeder. The second thing is electronics. Clemens has again done some amazing work on this version. The PCB monitors and controls up to 12 motors, 2 load cells, tons of sensors and encoders, CAN bus traffic, and scanner data, all more or less simultaneously. This is definitely not rocket science, but it's still much more complex than an average 3D printer or CNC board. The functionality of this PCB alone would normally be done in at least 15,000 euros worth of Siemens PLC stuff. Having spent so much time on fasteners, I can't tell you how good this feels. A single machine for all parts. Out of many reasons, this is such a hard problem. Yet somehow it works. And of course I'm annoyed that it's a complexity monster. But it could be simplified to probably half the axis, be much smaller and cheaper. But for now, I'm just going to enjoy that we have made a single machine to count all parts. And parts across such an enormous variety. Actually, there are many more things it could count. Lego, candy, cigarettes, the list is probably long. A normal video would end here, but since so much has happened since my last one, here are a couple of updates. At the end of last year, we were invited by Bamboo Lab to showcase our stuff on their booth at fromnext. Special thanks to everyone from the Europe team. I met a lot of you, and most of you were really nice to talk to. Overall, it was an exhausting but super fun week, and I had many interesting conversations with Stefan, Dr. Tao, people from Prusa, and many more. In the meantime, we designed a cardboard fastener shelf as a concept. Cardboard or packaging construction and design is such a weird but cool world. It's very similar to sheet metal in some ways, but in others not at all. At least for me, it's a completely new world, and we even got our own cardboard plotter. It's from 1995, but it was a really good deal, and it has been working great so far. It has 5 tools, and it can not only cut cardboard, but also create bend lines in it. I think in theory it should even be able to cut pre-preg carbon fiber, but I am not entirely sure about this. For packaging prototyping, it's an amazing tool. The cardboard shelf itself has a production cost of less than 2 euros, at least when produced in some volume, and I still think it would actually be a good product. But At least at the small quantities that we made, we were never able to nail production quality. And there was just so much going on that we eventually had to stop it. We also deployed our own mobile app for Android and iOS, which is connected to Shopify. And it really was a test on how to speed up the ordering of fasteners. Basically, the idea was that you can simply walk up to a shelf, scan the parts that you are missing, and add them to a simple queue. From a technical standpoint, it's really cool. In fact, it could easily be connected via the Shopify API to the feeders and let them start automatically. But really, David and Talha did most of the work on this and deserve all the praise. Now, I want to give you guys an update on what's happening. But there are a couple of things going on behind the scenes that I can't talk about publicly, at least at this point. But what I can say is that, to be honest, I am having a bit of a discussion with myself. I had underestimated how little is left here. In Europe and the US, there's almost no manufacturing left. If you take away food, cars, and defense, then really only a few crumbs remain. Technical performance aside, from a business standpoint, what we have achieved, considering the time spent, is simply not enough. In the last year or so, there have been 4 serious investment offers. I found 3 of them to be very sketchy, but the most recent offer came from the owner of a very, very big company. And to make a long story short, I really like the guy. Now, I don't know if this is different in the US, but at least in Germany, stuff like this takes at least half a year to go through. And we actually went all the way to the term sheet with them, but in the end they decided not to do it. And I spoke to him very openly about this, and I understand his concerns. I am normally immune to this, but in his case, I understand. There's truth in his opinion. I think as a company, it's totally okay when you have multiple problems. It's probably normal. Things get dangerous, in my opinion, when it feels like there is always just one problem left. I call it the hamster wheel. It's the situation where you think it's just this one technical thing that's missing, the one feature, just this one thing until the real breakthrough comes. We just have to solve this. But after you solved it, there's just the next, just this one more thing that comes along. And this is an infinite loop. Now, if this happens for more than 3 times, then I think chances are high you don't actually have a technical problem, but something else. And we are in kind of a similar situation. Our hamster wheel is that we think we need more machines to offer better kitting service to sell more. But this is stupid logic. The order is flipped. It should be the other way around. We should sell more to get more machines. Scaling should happen out of necessity, not as a purpose to... I know very good people who have spent 10 years running in the hamster wheel, and I'm not going to do that. Fortunately, we don't have money, so hopefully that won't happen to us. And also usually I freak out after a couple rounds of the hamster wheel. And I just realized that we were back in it again. But really my main concern is time. I think that what you won't achieve in 6 months, you also won't achieve in 6 years. And this is not really a question of money. We have tried each option around this machine for 6 months now. And technically, I think it was very successful. Economically, in my opinion, not so much. Now, I'm not pulling the plug now. I just think it's important to ask hard questions and to do that regardless of sunk cost. I have always said either we will take an entire market or the company will die trying. And I will remain true to that. You see, I don't give up easily, and that is the only reason some of my technical stuff works. But as a persistent person, it's very easy to get caught in a hole that only you yourself are digging. In university, I always regretted not dropping out earlier. And looking back at it now, it was such a painful waste of time. And I'm not doing this again. If it doesn't work, then it doesn't work. Now, I know this doesn't fit the typical YouTube hype positivity, but I think it would be wrong to do this video without my skepticism. No matter if we continue with the MPS or not, the videos here will go on with technical content. And I've got a lot of ideas. So anyway, this was a long one. If you want to see me build those prototypes, be sure to hit the subscribe button, and I will see you in the next video.